homework. We covered it as the last topic before the exam. We did one example on it in class, and it wasn't on the homework. So I wouldn't think it's going to be on the exam, which means knowing my knock, it will be on the exam. So I should study it.
Yeah,
I'm
see,
glad
I
did.
thought it was going to be on the exam, but just forgot to study it. And definitely paid the price because of the two problems. The first one, fine.
Oh yeah,
I know how to do that.
First one was basic string analysis. For
Second one, yeah, I bombed that one.
I think I made a slight arithmetic error because you know how sigma 1 and sigma 2 should be equal?
Right, so Joshua is online.
Sure.
Can you hear me?
Okay, well basically.
Oh yeah, it said they should.
Yeah, when I plugged in my values for my two different equations. I got
Joshua, can you hear me? Ah,
Nice.
It's probably a small error. He won't take up too many points from that because I have the concept.
do you have audio?
I spent
Josh?
half an hour trying to figure out how to, because one of the examples we did in class, we solved it via matrix method, and I have a fancy calculator. And I asked them ahead of time, because you know how the exam says no fancy calculators? So I'm like, I don't want to use this, I'm not allowed to, and it's cheating. So I asked them ahead of time, they're like, yeah, I know, I put that on there, but I recycled those cover sheets from previous semesters, and you're allowed to use whatever calculator you want. So I spent 30 minutes trying to figure out how to numbers into the matrix, and then I finally get it
Oh, Josh,
before the
can you hear
exam.
me? Check.
And then I go to the exam, it's like, oh, you don't even need to solve it via matrix because of the nature of the problem.
He's checking.
It's not like 30 minutes, because the only way to solve it, the example in class, is via the matrix method, which you need to use either a calculator or MATLAB for.
No.
Because I remember when we went over that example in class.
All right, Joshua, do you have audio?
At least you have a fancy calculator.
Yeah, I barely used it. I think the only times I bought that thing like freshman year of college, and I only used it for structure. And I only used it for 7 physics exams for that one problem, and then a couple of structure problems here and there. I've never used it for any other class because I'm not allowed to. All my calc classes are like, yeah, no.
Well, yeah, because all those things can integrate and stuff. So they can do calculus.
All right, once again, check. Josh, do you have audio? Can you hear me? Check. Okay, so let's begin with in-class attendance. You, Josh?
All I'll say is that we should have studied.
Okay.
I didn't study. I should have studied a little.
Because like, especially after how long, it's just as you know coming in here, and after how long you start covering it, you think of it. I'm mad at myself for losing points on a simple, easy problem. So.
After the exam, I do remember this. I don't remember much about it, but I do remember that after the exam, I realized that I probably fucked something up.
I wouldn't be surprised if I did that. That's not
Why?
All right, so I still don't know if I have audio or not, but Josh, can you hear me? Can you react or something? Can you react? Oh, okay. So you're hearing me. Okay, good. I appreciate that. Please lower your hand. Okay, good. Okay. So looks like he doesn't have audio. Good. Oh,
What the heck was that?
am I hearing it?
No, that was my phone.
No, sorry. It's okay. Let's move on. So exam 1, I have to apologize. I haven't completed the grading yet. I'm probably about 65% done. I started with the other section, so the other section is done, but this section, sorry.
Oh.
not
Oh,
quite
I
done.
see how it is.
I would rather go slow and happy mode than just rush it in and hush everybody kind of. I don't want to do that. I want to spend more time kind of read between, right? Because sometimes I have to. And then I'm not going to be so harsh on, oh, you don't have units for this number, unit for that number kind of thing, because I know some of you forget about, I go easy for those. I'm going to be super picky for homework and quiz because you should have plenty of time to, take care of those details. But, on exam, no. Okay. So again, I try to get it done by the end of today. So as soon as I finish up, I'm going to give you announcement, class average, and other things. And the solution is already up. Okay. So I don't think I have to go over it, but those are all taken straight out of something. This is section 3. So section 3, problem 1 is, it's a quiz 1A or B, either way. This is like a US unit. Car tire thing. Right? It's like a cut and paste and change the number. Yes. That's it. Yeah. That's all. Problem 2, this is, I think, quiz 3, static pressure is minus Q. Of course, you know that. Some of you didn't know. That means, well, wait a minute. Did you understand the basics? This is minus Q, right? That's right. And this is something, I made up like a conversion duct. This is high speed, so you have to use energy equation, not the real number. Yeah, so it's very simple. Anyways. So I don't think I have to go through. Those are all taken straight up from something. Okay. Anyways, so far I guess I didn't see anybody who really screwed up. So that's an encouraging one. I saw some 30 out of 30s. That's great. Yeah. So no problem. I'm not worried about anybody. Unless you receive my email saying, hey, you are doing poorly, you should drop this class kind of email. If you didn't get that kind of email, you're okay. Don't worry about it, okay? Do you have any question about exam 1? You're okay. No problem. If you're not okay, you probably know it. Okay, so question, Mike.
Will we ever get our exams actually back? Or are you just gonna, or do we just send
suppose if I complete your grading, the graded work should be in the OneDrive, you can see it. Some of you actually can see it. If your last name is like a first end of alphabetical order, like kind of
Mine's bad.
P, you're P, so you
Yeah.
always start with on top. So some of you actually have a graded work in OneDrive, you can see it. Okay. For those like who's like a really late, you're late, really alphabetical ones. Okay. and DJ is always right, of course, because sorry. Anyways, don't worry about it. Okay. So today we are going to move on. Continue Unit A5. So Unit A5, we talked about coefficients last class. Before the fall break and midterm exam, we talked about how the pressure and shear stress distribution over the surface. You're going to integrate from leading edge to trailing edge, and then break it down to normal force, actual force per unit span. And then with an angle tag, you're going to determine lift and drag and moment at any location. So I guess the important thing is we talk everything based on coefficients. We're not going to talk anything real number, including the distance also, okay? So you're talking about just x. By the way, we are looking at the 2 different coordinates for this. So this is a very unique for airplane coordinate system. It could be cross-section of a wing called airfoil or wing itself. Typically, we choose leading edge as a coordinate origin, and then choose either x or s. Okay, x or s, all right? S is sometimes called streamline coordinate system coming from fluid mechanics. It's typically curved path. Now, suppose if you take, what is that? Potential flow theory, which is coming up unit B, potential flow theory. We are going to do full-blown mathematical analysis of flow field. We are going to choose this kind of path. Okay, so one of them, it could be like an upper surface. The other one is lower surface. But we can represent those things as one of those streamlines. Now we are going to probably understand later on, streamline that actually goes through the stagnation point is called the stagnation streamline that actually represents the surface of a body. You're going to discover that project 2A, by the way, when do you want to turn in project 1? Project 1? Please tell me that. When do you want to turn in project 1? When?
I say,
You say
this week, Friday.
Friday. Anybody else?
Monday next week?
Monday next week? Anybody else?
December 15th.
Which week? What? December.
December 15th.
Never.
Project 2A comes earlier. Anyways, either way, right? Looks like. Who goes for Friday? 1, 2, 3, 4. Okay, Monday. That's it. So Monday next week is gonna be project 1 due. I'm gonna announce it. Don't worry about it. Okay. So let's continue discussion. So we are going to deal with 2 different coordinate systems always, so be careful about that. One is the coordinate which represents the surface. Could be upper surface, could be lower surface, okay? So this is a streamline coordinate curve to pass. We are going to use that. Okay, later on you're going to deal with flow of a circular cylinder. If this body is a circular cylinder, this can be represented by better coordinate system. What kind of coordinate system do you choose if this is a circular cross section? Okay. 2D coordinate system, you can pick it up to represent this surface, this surface. What kind of coordinate system? Polar coordinate system, of course. I didn't say it. So polar coordinate system comes in, okay, you use it all the time. The other coordinate system is, of course, starting from leading edge toward the trailing edge along the code. Okay, so this is X. So either X or S, you are going to always do coordinate transformation. Here we go. This is the coordinate transformation. You have to do that all the time. One is curve to pass called streamline coordinate. Later on, if it's cross-section circular, this is going to be polar coordinate system. The other one is X, which is Cartesian, which is essentially body attached, measured from leading edge to the trailing edge along the code is X. Now, even though we're not going to use X or S, typically we are going to X divided by C, make it dimensionless. Okay, so we're going to know later. We oftentimes X divided by C, X over Y. This is normalized coordinate. By using this, suppose if you want to say quarter code is 0.25C, or 25% measured from leading edge is called quarter code. 50% code measured from leading edge is half code. Okay, X over C is 1 at the trailing edge, 0 at the leading edge. So every number is between 0 and 1. That is normalized coordinate. If you want to download airfoil coordinate information data, everything is normalized. Number is between 0 to 1. 0 being leading edge, 1 is being trailing edge. Why is that? Because you can download the shape and multiply by the actual code to represent any size airplane string. Okay? It's the same shape. It's just a different size of airplane. Same shape. Right? We want to normalize. So it's independent to the size. Suppose if you want to create this kind of small diameter airplane or actual size airplane, it's the same cross section, but it's just different code names. You can represent both. Okay. So everything is dimensionless. Be careful about that. So other things here. Obviously, we looked at the 2D airfoil. This is coefficient. This is lift coefficient, drag coefficient. This is moment coefficient. Now moment depends on the location, so always comes with subscript. CM at the leading edge, quarter code, half code, trailing edge, whatever. Those will be different values. Okay? Moment will be different values. So you need to have subscript, always location along the code. Okay? So let me just put it. So you need to have subscript. This is the location along the code. Okay? You need to always have that. And also even pressure distribution, you measure the pressure, P. However, you're going to normalize the pressure by subtracting P infinity, this is a free stream pressure, divided by Q infinity, which is a free stream dynamic pressure. This is going to be coefficient. Now, one quick observation from CP, okay? Suppose if the pressure P is equal to the free stream static value P infinity, what is the CP at that point? In other words, that's the static port. At the static port, you sense the pressure P go to P infinity. What is the CP at the static port? 0. Yes. CP equal to 0. This is called static port. Okay? You're going to run that. Don't worry too much about it. What about the stagnation point, where the velocity becomes 0? What's CP?
Undefined.
CP is 1. CP is 1. CP is 1. Okay? This is called stagnation point. Can CP becomes more than 1? Yes or no?
No.
No. 1 is the absolute largest value of CP. You cannot have CP 1.2. You can laugh at it if somebody says, "This no such a thing. What are you talking about? CP 1.2? Huh?" That's your reaction. CP 1 is a stagnation point. That's absolute largest. Can CP go negative? Yes. It could be huge negative. Okay. If the CP negative, what does that really mean? That's a lower than atmospheric pressure, so that's vacuum. So when you have lower pressure zone formed up, CP becomes negative value. Okay, stagnation point, CP is 1. Okay, so those are the important things later on. We are going to plot the CP distribution over the surface, not the pressure distribution, but the CP distribution. Then integrating CP to get lift and drag and moment, as we did it in last class. Go ahead.
Is the leading edge on all the way to the left side?
This is leading edge.
Okay.
Okay.
That's where 0 is.
X over C is 0 at the leading edge. X equal to 0 at the leading edge. Yeah.
Okay.
Any other question? So be careful about lowercase and uppercase difference. Lowercase is 2D airfoil, and then lift is all part unit span. This is a unit span. Okay. So you can actually do 3-dimensional wind tunnel testing with a constant cross-section model, and then measure the lift and drag, pressure and all that, and divide by span of 1 span, and then making it unit span value of lift and drag and moment. So those are 2D coefficients, lowercase both. Okay. Pressure coefficient, and also if you measure tau, obviously. Now, typically in low-speed wind tunnel, you cannot really measure skin friction, or this is a shear stress. It's very difficult. Probably not possible. But anyway, suppose if you have that kind of information, you can normalize it to have a skin friction coefficient. Okay, so everything is either coefficient or normalized value. Dimensionless is the point. So that's why you're working on your quiz, right?
Yes.
That's all about dimensionless. Why do you need dimensionless properties? Why those are so important? Because you're dealing with smaller scale tests that predict actual size. Yeah. So everything what you measure and you talk about is going to be dimension independent. Okay. Dimensionless. This is important. It's coming from fluid mechanics. Okay, so it's important. Go through quiz 0 problem 6 or quiz 6. Okay. Any question, anybody? So today we are going to talk about 2 important locations, difference point of airplane / airfoil. One is a center of pressure, CP. One is aerodynamic center, AC. Those are different. Very, very important. Center of pressure. The other one is aerodynamic center. Now, before we even talk about that, For airplane design and performance analysis, we rarely use this. We always kind of use this. And then also another important information that you may know it, but aerodynamic center is about quarter code. Not always, but very close to quarter code, okay? Before we talk about what it is. Quarter code. At least very close to quarter code. Actually, if it's thin airfoil, it's called thin airfoil theory. Thin airfoil theory says aerodynamic center is quarter code. You can find out by going through thin airfoil theory, which is actually course materials, which is optional. Thin airfoil theory, optional references for your own self-study purposes only. Now nowadays, I no longer cover this. But thin airfoil theory actually do a mathematical derivation of a thin airfoil, and then it basically says that quarter code is aerodynamic center. Thin airfoil means that the thickness you're going to completely ignore mathematically. That's called thin airfoil theory. Okay. If you're curious about, interested in, please go over it by yourself. It's not required material. No, let's go ahead.
What, just a brief summary of how thin is thin? Like quarter inch? Okay.
It's always gray.
Okay.
Oh, this is thin enough, but do you really think so? Kind of thing. Thin airfoil means this is a 100% academically analytical, completely ignore the thickness. So you only talk about the camber line, camber line. Okay. So suppose you have a cambered airfoil. It's kind of way too early to talk about. Airfoil may have a camber. Camber means non-symmetric cross-section, okay? Now, you can draw a straight line between leading edge to trailing edge. Straight line is a code, right? So this is a code. Straight line between leading edge to trailing edge is a code. But at the same time, if this is cambered, you can draw a line in between upper and lower surface. In other words, intermediate lines between upper and lower surface. You can draw that kind of line, okay? This is called mean camber line. So thin airfoil theory literally means that we are going to think about the flap plate with the mean camber line shape. That's thin airfoil theory. There's no thickness. It's a flap plate with bent flap plate. It's thin airfoil. So thickness is completely ignored. That's called thin airfoil. Anyways, we talk about that a little bit later after we cover 2D airfoil theory, Unit C. Okay. We actually have a classic videos I'm going to show you too. So let's find out, first of all, center pressure, even though we rarely use it in aerodynamic analysis, flight mechanics. This is kind of sad, it's useless, but this is something you know from fluid mechanics. That's why we start from. Have you ever heard of center pressure from fluid mechanics? Please, somebody tell me. Where did you find center pressure? What is it? And then where on earth, your fluid mechanics teacher covered that center pressure? Like under what subject? Go ahead.
It was usually an object underwater or something like that. And
Oh, great point. Let's take a look. So let's take a look at unit. I think unit B4. Yeah, this is very famous fluid mechanics stumbling stone hydrostatic force. Here we go. Hydrostatic force. You submerge something underwater. You see that? You submerge something under like a bottom surface and side surface of the fish tank. This portion is submerged under the water, and then of course because of the pressure distribution, you develop hydrostatic resultant force that actually goes through where? For the bottom, yes, but on the side,
2/3 down.
2/3 down. Where is that 2/3 down location called?
Central.
This is not centroid of the surface. This is called center of pressure. Okay. Do you remember that? Center of pressure is the location where the resultant force acts through without the moment developed with it. It's the same thing. Okay? So same thing. We're going to go back and redefine center of pressure to begin with. Center of pressure is, okay? Of course, you can develop normal force and actual force. This is the resolved force into perpendicular and parallel direction to the code of a resultant force. Resultant force is developed out of the distributed pressure and shear stress, right? Right? And then you can place the resultant force in any location along this code, right? Right? So suppose if you choose the location right here where there's no moment developed. It's called center of pressure. Let me repeat. Okay? So resultant force. I'm going to go back once again to the top of A5, all right? Okay, top. Here we go. So this is the first page of unit A5. Of course, we know because of the pressure and shear stress distributed all over the surface, you can integrate from leading edge to trailing edge to determine resultant force, and then this resultant force can be placed at any location along this code. Okay, so you can put it here, leading edge, quarter code, half code, trailing edge, whatever you want to, but there is a location where along this code, this moment disappears. Okay, that's the location called the center of pressure. Can you do such a thing from statics? Yes, you can. Sure. Typically, that is the centroid of the distributed loading. Is that correct? But, you know, in this case, distributed loading is so non-uniform and not linear, so it's hard to understand that. So you're going to find out center of pressure location by knowing the fact that this moment becomes zero. That's the location called center of pressure. Okay? So we are going to find that center of pressure to begin with. So center of pressure. So now you are given three different figures. Let's call this left figure. This is called center figure. This is called right figure. Okay? So you're going to put normal and actual forces. Let's say this is zero angle of attack. If it is zero angle of attack, normal force becomes left, actual force becomes right. Let's just make it simple. Okay, zero angle of attack, left and right. So those two pair of forces can move around from leading edge to trailing edge along this code line. You can move around. So this is the case that the lift and drag placed at the leading edge, of course, it is associated with leading edge moment per unit span. Sure. And let's just move it to the quarter code location. And then you're going to come up with a different body of moment at the quarter code per unit span. Those are different bodies. Then you shift it around to find out the location where those moment becomes actually zero. This is called center of pressure. So as you run very well from statics, those three are all equivalent. Equivalent force and moment system. Is that correct? Okay, yeah. So you can say this equal to that, this equal to that, this equal to that, all equal to each other, right? Okay, so having said that, I'm going to basically come up with the equation. Go ahead.
As you shift down the chord,
As you shift
between
down
the figures, yeah, like that, does lift and drag change, or is that constant all the way through the chord?
Only moment changes.
Okay, so lift and drag
Unless you change the direction of those two. If you change those, yeah, it's going to change. Okay. Those are all equivalent. Equivalent moment and force system. Okay. So let's consider each one of those figures. Let's consider developed leading edge moment. For each configuration, okay? Now, interestingly, you don't have to choose leading edge. You can choose any location, by the way. You can choose what is the moment at the quote-unquote, that's fine too. But anyways, leading edge is the easiest. But it could be trailing edge, could be fine. But anyways, for this figure, how much leading edge moment do you have, of course? M prime LE. So I'm going to have left figure, center figure, and right figure, okay? So left figure, leading edge moment is developed M prime LE, which is equal to, let's take a look at center figure. How much total leading edge moment is developed for this center figure? Anybody? Is it pitching up or pitching down moment?
Reaching out.
Drag doesn't create any moment. It just goes through the leading edge. How about this?
Pitching down.
This is going to create pitch down moment, yeah, at the leading edge. And plus, of course, this one is pitch up moment. You just add. So you have two things added together, right? So this is going to be pitch down moment negative. Moment arm is quarter code times L prime. So this is going to be pitch down moment created by this lift force at the leading edge. Do you follow that?
Oh, question.
What?
Is it pitched down? Can you apply the right hand rule to this?
L times this pitch down, right? Do you see that? Moment. Statics. Statics. This is moment arm. Pitch down moment. Okay? Minus, because pitch down. Plus, okay? M prime, quote unquote. This is pitch up moment, already given here. So those two added together is going to be developed leading edge moment of the center figure. Do you follow? Do you follow? Okay. Right hand figure here. So what about the moment developed at the leading edge? Minus would pitch down L prime times this distance. Okay? Pitch down moment at the leading edge. So this is going to be negative. Moment arm is XCP. L prime. By the way, prime is per unit span, okay? So those are all equal to each other. So now you can squeeze out three equations, actually. So this comes down to series of three equations. First equation is M prime LE is equal to M prime quarter code minus quarter code times L prime. This is equation 1, equation 2. M prime quarter code minus quarter code times L prime is equal to negative XCP times L prime. This is equation 2. Equation 3 is M prime LE is equal to minus XCP L prime. This is equation 3. So 3 equations comes up. Okay? Now, if you look at equation 2 and 3, this is going to solve XCP. Equation 2 basically gives you that. XCP is equal to, somebody please tell me?
LE over L prime.
That's right.
Minus.
Minus M prime quarter code divided by L prime. So this is the location of center pressure in terms of quarter code moment and then lift per unit span. If you use the equation 3, this also solves XCP, center pressure location, which is equal to negative M prime leading edge divided by L prime. So this is the center pressure location in terms of leading edge moment and lift per unit span. 2 equations comes up. Those are called center of pressure location. Okay. Now, what about equation one? Equation one, what's the meaning of it? Anybody?
You can solve for either leading edge moment.
That's right. So in other words, okay, so this actually relates the moment at the quarter code and the leading edge. Is that right? So if you know one of those, you can get the other. Sure. So this is a relationship. Lots of people actually forget about this at the final exam time. Because I can pick up this relationship as an external, extra information to solve the final exam, which is kind of important. It seems impossible to solve, but whoa, don't you remember this? If you're given leading edge moment, you can get quarter code moment. If you're given quarter code moment, you can get leading edge moment. Period. This is a relationship. Okay. Relationship between leading edge and quarter code moments. Important information, people actually forget about it. Okay. Any questions here? So this is called center of pressure location along the code measured from leading edge. So we are going to move on to the next page. Let's just find out actually center of pressure locations. Okay, next page. Okay, can we move on? Can we move on?
Yeah.
Next page. So let's take a look at the class example program 851. A set of experimental data for a series of conventional airfoil is available. Yes, this is called NACA conventional airfoil data. Do you know how to look it up? Let me show you. Did I actually? Course material include that maybe? NACA conventional airfoil data. Here we go. If you click on that, you have a bunch of data sets. And this is me. Looks totally young. I made up this website a long time ago. 10 plus more years ago. Go ahead, question. Those are data sets.
What do the digits mean?
Yeah, you're gonna find out in Unit C. This is NACA 4-digit, 5-digit, and 6 cities. We're gonna cover those things later. Don't worry too much about it right now. But bottom line is, you have a data set available, okay? Then, well, just to click one of them to find out what it is. Whoa, this is data set. Have you ever seen that? This is NACA conventional airfoil data set. Well, this is like a hand plot, right? It's not Excel plot. So people plotted by hand in 1950s, and it was not even NASA, it was NACA. Do you know NACA? Before NASA, there was NACA. National Advisory Committee for Aeronautics. Okay, 1950s. It's like a form right after World War II. They did huge amount of wind tunnel testing, compiled the data set for the standard shape. So it's one of those things. We're gonna find out in Unit C. Don't worry too much about it. But having said that, this is the data set. Okay, you can read off. Okay, so this is the angle over time. Okay, good. How much lift can this airfoil cross section produce for, I don't know, 2 degrees angle of attack? Oh, it looks like 0.4 CL, lift coefficient. This is the shape. This is called NACA 4412 cross section, one of those standard shape, 4-digit. Okay. So this is NACA 4412 is one of these NACA conventional airfoils. We're gonna cover that, don't worry about it. Okay, later. And it shows the following data: angle of attack 4 degrees, lift coefficient 0.8, you can expect. CM quarter, what's this? CM quarter, what's this? Is lift coefficient, what's it?
That's the more.
Quarter code moment coefficient minus 0.1. Oh, okay, I get those kind of data set. What is the location of the aerodynamic? No, location of the center of pressure. What is that? Looks like quarter code. Ooh, let's just pick up the equation those are the equation we got. Can we use those equations? Well, one of those, I guess. One of those involve quarter code, yeah, quarter code. Can we use this equation? Plug and check. What's the problem? Go ahead.
We only have the coefficient, we don't actually have the actual moment.
That's right. This is actual moment, isn't it? This is actual lift per unit span, isn't it? This is actual code length. We never know those things. So we have to normalize it. How do you have any idea how to normalize this? Okay. Go ahead. Go ahead.
The chord length? Or...
Divided by chord length, correct. That's right. So let's just to find out. Okay, starting from this equation. Okay. So XCP, this is actual distance, is quarter code minus moment at quarter code per unit span divided by diff per unit span. So let's divide this equation by chord length C. Okay? Then we're going to call this XCP over bar. This is normalized distance, which is, okay, now it becomes 1 over 4. This is 0.25 minus, so this is going to be M prime quarter code divided by C. This is L prime, okay? So continues, XCP over bar is 0.25 minus, let's do something. Let's just do something for those. Any idea? Go ahead. Can you do something here? Divide both denominator and numerator by Q infinity C. Let's try. Both denominator and numerator, divide both by Q infinity C. You're going to have this, okay? M prime quarter code divided by Q infinity C square. This is L prime over Q infinity C. So question is, what's this?
CM. Or
And then
CM
what's
chord.
this?
CL.
This is CL, lift coefficient. What's this?
CM chord.
CM quarter code. That's right. Okay. So as a result, you get equation which is XCP divided by C, which is called X over bar CP, normalized coordinate, which is 0.25 minus CM quarter code divided by CL. Now you can now plug in the data set, which is given CM quarter code is minus 0.1 given, drift coefficient 0.8, in which this is 0.375. So X over bar CP for this case is 37.5% code measured from leading edge. Okay. This is independent to how big your cross section is. Normalized, which is dimensionless answer. This is what we want. Okay. So this applies for small scale, large scale, medium scale, any scale, because it's dimensionless. Okay. So this is a location called center of pressure, normalized value, 37.5% measured from leading edge. Okay. 0.375. Now, similarly, you can do this, okay? In this case, obviously, quarter code moment coefficient is given. Now, if you're given leading edge moment coefficient, you can use this equation, similarly. XCP over bar can be given by minus CM taken at the leading edge divided by CL. The same similar kind of equation. Okay. Now in this case, you cannot use this equation because you don't know leading edge moment, but you can relate leading edge to quarter code moment. Okay, you can do that, of course. Now you are going to end up having the same equation. Okay. So any question here? This is how you determine center of pressure. Now, center of pressure, like I said, we rarely use it. Do you know the reason?
It's not particularly useful.
CP location. What is the important thing? depends on angle of attack. This case, alpha is equal to 4 degrees. Alpha equal to 4 degrees. You have 37.5%, but suppose if you pitch up to 8 degrees, do you think the same location? No, it's going to change. If you change it to angle of attack 2 degrees, do you think it's still 37? No, it's changed. Changes and changes all the time. As you pitch up and pitch down, center of pressure changes all the time. We cannot use that as a reference point because it depends on angle of attack. That's why, go ahead.
I was gonna ask, should we make it a function of angle of attack?
This is a function of angle of attack. Center of pressure is a function of angle of attack, and it's not the linear function. Every angle comes up with different location. Go ahead.
Does the center of pressure location always stay on the chord line?
We choose chord line to measure the location. So that's what we decided to go. So that's the difference. So difference line is a chord line. So you can choose any location along the chord line. But along that chord line, it just keeps changing with angle of attack. That's the center of pressure. So do you have any other idea to have some better difference? Aerodynamic center, that's one. That's the idea of aerodynamic center. So basically, aerodynamic center is a fixed location. It's a big difference. Okay, so this is we want to defer to something. Difference point. Difference point for flight mechanics or airplane design, either way. Okay. Because center of pressure keeps changing, we don't want to use that. Instead, we want to use some fixed location called aerodynamic center, and then usually close to quarter code. Not exactly. Each airfoil comes with slightly different value, but it's very close to quarter code. So it's kind of safe to say, if somebody says, what is the aerodynamic center? It's the easiest choice of answer is, oh, it's a quarter code. Give and take a little quarter code. That's what the airplane designer talk about. Okay, so we talk about aerodynamic center next class. Go ahead, question.
So since it's very close to quarter code.
Quarter code.
Yeah. Since it's very close to that, what is the reason of it not being absolute?
Not absolutely quarter code.
Yeah.
Oh, because it's not a quarter code exactly. If you're talking about very thin airfoil, it's quarter code period. But as you apply the thickness, as you apply the more camber, it is going to change slightly.
I see.
That's why. Okay, we're gonna find out.
Is that only true for Hershey bar wings? Because I was thinking that Delta wings would have a different.
That's actually 3D effect.
Okay.
So we cannot talk about it until we hit 3D link.
Okay.
That's gonna change, yes.
Okay.
My answer is yes, but it's not as simple as this. So you're right, because we're talking about aerodynamic center of airfoil.
Yeah.
Yeah. So it's a Hershey-bar wing of a unit spec.
Yeah.
Yeah. Any other question? Go ahead.
Is the aerodynamic center generally found like behind, like to the right of like?
Actually, aerodynamic center is at the most quarter code. It may shift slightly forward if you have a thicker wing.
So it can only go left.
It can only go this way.
Okay.
Now the figure says, well, yeah, that's right. Yeah, it can go. Yeah. Yeah. Any other question? Slightly shifted forward. If you have a thick airfoil or highly cambered airfoil, it cannot go beyond the quarter code. It's a good sanity check. Any other question?
So
Yeah.
what do you use aerodynamic center for what purpose in comparison to just knowing the center of pressure?
In other words, you want to determine where the lift is acting on. In other words, lift is acting on aerodynamic center. That is going to create the control moments measured from center of gravity.
Got it.
That's it. That's a flight net.
Okay.
So airplane trying to kind of lower the elevator, try to pitch up kind of thing, how much moment is generated, measured from center of gravity to the aerodynamic center, because that's where the lift is acting through.
Okay.
So that's flight mech question. That actually determine your airplane becomes stable or unstable. If you try to pitch up, airplane try to pitch down by natural tendency. Okay. Any other question? We touch a little bit touch base of that because this is not flight mech craft, but we talk about those things. All right, so let's stop here today. So next class, we're gonna complete Unit A5 with aerodynamic center. And then we're gonna move into Unit B2. By the way, before you go, Unit B1 is not lecturing class, right? You should know that, okay? So this is YouTube lecture, Unit B1, I'm not gonna do lecturing class. So please go ahead, take a look at it. So next class, we're gonna possibly go into Unit B2. If you have a question, I'll be happy to answer anything. All right, so have a good day. See you guys back on Wednesday.
Are you heading to your dorm?
I'm going to the library and I'm gonna go get a side meeting all day.
Oh, okay. Don't worry about sending me the thing then.